我拿起来就有，原来就是有用的。
咖啡啊嘛，咖啡有运营，它便宜，还知道那个 DNS 快递。
看懂了，我自己以为我们没有，他去那个这样草，他
然后马上怎么聊起来？
Okay, so welcome back to the last lecture of this course. I will do some announcement first. So next class, this class will be held in D2LP01. So and the time would be from 11 p.m. to 2 p.m. Yes, so this class will swap with Nicole's because Nicole's I think it's going to I think it's Spanish, I don't know, and the flight will be arriving in Hong Kong around 12 a.m. So she will be in here with you at 2 o'clock. So for the group that is going to present today, is going to present next week, you need to get prepared by 11 a.m. Okay. And also you must come for next class for to fill out the course evaluation form as well. And for the individual assignment, you will write a 1,500 words report about your group project, and the submission date is 12th of May. So you have the whole day to do it. Okay. And it should be consist of, I think, around 5 parts in introduction, deployment, evaluations, and some recommendations of your project and reflections. You should add reference to your essay and maybe some appendix as well. And for the group project, the presentation time is around 15 to 25 minutes with a Q&A section. And the submission date is the same as the written report. So I think the most important part of the group project is to have a screen captures or a video recording your project, because this is how we know you actually did the work. And you should also write some documentation. So for those groups who haven't actually run any code in the server, please fill in this schedule for next week, because I need to take the screen captures or video of your project. And if you have not run any job or any models, I cannot take a screen captures of your video, of your demo and of your project. So by the end of today's class, you must, if you have not run anything, you must schedule a time to run your demo for next week. So this time slot is for those who might want some consultation today. It might not have to be 15 minutes, but if you have not done anything at all, which I've seen some group have not done anything at all in the HPC server, I strongly recommend you to schedule a time slot in the next week so that I know you have something to submit. Okay, so today we will be talking about image generation and video generation and some basic maths about the generation task. So you will be using all the knowledge you have learned to understand image generation and video generation. So let's go back a bit. So I've talked about KL divergence earlier, and I'm going to refresh your memory by starting with the probability distribution. So essentially, all the course materials that I've talked about is revolving around the central topic, which is the KL divergence. Essentially, KL divergence is originated from a probability distribution. So essentially, you have a probability distribution over a set of outcomes, and dx often notates the true population or the true data. And you have another probability distribution, which is your model. And the key idea is for every generative model, it is tries to make the Q of x the same as the P of x. So you try to shift your model distributions to the true distributions. Okay, so how do we do it? It's actually, first we have to measure how much the model distribution diverges away from the true distribution. And with this, we have a special meter or special device called KL divergence, which measures the statistic distance between the two distributions. So, because it is very difficult for you to use a straight like a ruler to measure the distance between the two distributions, so we use a special tool called KL divergence to measure. And we have mentioned the surprise. So KL divergence uses a concept called surprise. So when you have a rare event first, you may be more surprised. They measure the surprise using a special formula. Here it's called minus log of P. It's just a definition. So it is a definition mathematically of surprise. And KL divergence simply measure the extra average surprise from using the wrong model. So this is not new. I think I've talked about this before. So an event with probability of a small probability would give us a big surprise if you see it happen. Say for example, if I study very hard in the for the exam and I expect I will get a very high grade, but unfortunately I failed the test. This kind of event will be considered as a big surprise, right? So it is the model that you have of the actual world is mismatched. So you have a bigger surprise. And if you plug in 0.01 in here, and you take the log of it, and take the negative log of this, if you give you a number, say in here is 4.6. So this measures the amount of surprise. And an event with the probability of, say, a high probability will give you a low surprise if it actually happens. So essentially, I will be asking a question. On average, how surprised am I when an event follows P and I know it is P? So this is the baseline of the actual world. So the uncertainty of the data itself. You can measure it with this formula. So this one just represents taking the average. So sum of all the possible events with its probability multiplied by the surprise defined in here, so which is called the entropy. You can also think of it as the uncertainty of the actual world. And I'm going to ask another question, which is more realistic, which is how surprised am I when events follow P, but I mistakenly use my model Q to predict it, and how much surprise will I get? And because the real world data often, because we only experience the real world data, so this term does not change. This term is taking the average of the actual probability distribution. And this term is the surprise if my model is wrong. So by subtracting the first term and the second term, we will have the extra surprise that our model is expected to give us. Okay, so rearrange the formula, you will get this final equation, which is the KL divergence. So subtracting the baseline from the cross entropy, which remains purely the penalty for Q instead of P. So this is the cross entropy minus the actual, the expected, the inevitable surprise that we will be experienced. And then, so this is essentially the KL divergence. And we can simplify the terms by factoring out the expectation term, and then we will arrive the standard KL divergence formula, which is the log ratio of probability of P over Q. Okay, so which quantifies how much more surprise each event is under our model. Okay. So it is kind of important to know that KL divergence is not symmetric. So it is not like a distance. If you swap the P distribution with Q distribution, it will give a different value. And the main reason essentially is that each direction weights the regional differently using so essentially because we have to follow the true distribution of P in the real world, and the model is just a model, so we will be not following this model. So what is important is actually in the real world, and therefore we will be weighted more on the surprise that we will find in P. So in this course, we will be focused on the forward KL divergence. So because this blue line represents the true data distribution, and this orange line represents the Q distribution. But what we are focusing on, or what we actually experience, is the real world. So the expected surprise, the expected average surprise is in here. I will give you a very simple example to understand this. So assume the x-axis is the difficulty of an exam. So if you are well prepared, so with your own model, you expect the exam will be like in that kind of difficulties. However, in the actual world, the exam is not that hard. So then the amount of surprise that you will get is this one. However, if the exam difficulties matches your expectation model, the surprise that you will get is not as high. So that's why the amount of surprise is not symmetric. The amount of surprise weighs more according to the blue distribution. Okay, so that is essentially illustrating what I've just said. Okay, so in summary, the KL divergence measured the statistical distance between two probability distributions and try to quantify how far a model distribution deviates from the real data. Okay. And the learning training objectives in machine learning always try to minimize the KL divergence. Sometimes they do it in the latent space, and sometimes they do it in the raw data space. So, but all in all the machine learning objectives is trying to minimize the KL divergence between the true distribution, this blue line, and the orange line, your model distribution. Okay, so that's bring us to the score function, which is how do we actually find a way to shift our model towards the true distribution. So essentially, how do we find the direction it's this blue arrow would take us? One simple trick is just to differentiate the KL divergence with respect to our model parameters. So this is these differentiations. You should be familiar with this differentiation by now because every backpropagation is essentially doing these differentiations. In here, we of course let the true data probability distribution to be a fixed target distribution, and let the model parameter be the parameterized model. And the forward KL divergence is simply differentiate this equation using theta. So because this term have no theta in it, this term is essentially just the unavoidable entropy of the actual data. So you can think of it as the noise inherent in the real world. So this is not actually important. What is important is the second term. How do we tune the parameters of our model? And so essentially you differentiate using this equation using the theta. The theta is the weight of your neural network in this course. So the gradient of the KL divergence is exactly the negative expected score function. So we define a new function here. The term is called new score function, evaluated under the target distribution P. So in this way, we can minimize the KL divergence with respect to theta. Is therefore equivalent to driving the expected score of the first term to 0. So the score function, what the score function tells you, the score function actually tells you at every point in the high dimension space. The score function tells you which direction to move towards the real data. So this is the gradient of the log probability density. And you can think of it as a vector field. So at every point x, it gives you a direction and magnitude point towards the region of higher data likelihood. So I think you can play around with this little app to understand more about what a vector field is. Okay, so essentially what a vector field is, so you is for every single point in this space, you will have an arrow pointing towards the true distribution. So if the vector space change, the arrow will be with different direction and with different kind of values. Okay. So this is what a vector field is. So in diffusion models, the exact same idea applies. But now the two distributions are the true target distribution, which is the real data distribution, where the actual image lives, and your model distribution. So from start, your model looks like a pure Gaussian noise, and every pixel is independently and random, so completely uniform across the space, and there is no structure and no meaning. So you can use KL divergence to help to train your diffusion models. So the objective of a diffusion model is to learn the path from moving your model Q to P, starting from pure noise, and gradually moving towards the real image distributions. And it is equivalent to minimize the KL divergence. So if you sample a noisy sample X that is somewhere between the noise and the real image, it will tell you which direction you should move to get to a real image distribution. And the direction is exactly the score function. Okay. So up till now, we have not talked about neural network. We just talked about this model with parameterized model. In here, we use the neural network differently. So we will be using a neural network to actually estimate the score function at every point. So we started with a pure Gaussian noise distribution, and we will train the neural network to guide our points towards the destination. So in diffusion, in the original diffusion model, the neural network is neither the true data P of x, the true data, nor the Q of x. You might be surprised because if you listen carefully, we mentioned that we try to parameterize the Q distribution. But in the diffusion case, it is slightly different. The neural network only tried to learn the mapping between the two. So fundamentally, the neural network is trying to learn or estimate the score at every single point. So it takes a noisy example as input and predicts directions, and it said, go go this way, this will reach your main destination. Okay, so in summary, this score function is the gradient of the log probability density pointing towards the true data from the random noise that you originally have. And diffusion models learn the score function directly through a denoising network, avoiding it to compute a intractable normalizing constants. So the neural network is acting as a compass in the noisy space to try to predict score at every noisy level to guide your point iteratively, step by step, towards the real image. So in here, the neural network actually outputs the arrow instead of directly moving your point to the actual point. So the arrow is what the main objective of the neural network. So as I've mentioned, now we have training data. So we have the input as for our neural network is a noisy image X, and the neural network outputs a score function, a direction, which is the same shape of the noisy image. And we will force the neural network to learn the directions. So in the training data set, we will try to train every possible noisy image defined, and the output would be the actual score function that we compute from the real image. And after this, we subtract the noise, and subtracting the predicted noise from the noisy image, and this is essentially equivalent to climbing up towards the true distribution of the data. Okay. So this is the generating steps. So we start from a noisy image, and then we use the neural network to predict a score function, and we climb towards step by step towards the space where the real image lies. Okay. So there are some different terms in here. You might want to dive deep if you want to do some research after this course. This term is essentially you can think of it as an exploration term in the noisy space. Try to kind of stabilize the iterations. So the neural network actually predicts the drift terms, and it tries to inject the right amount of noise so that it's kind of moves correctly towards the true data distribution. Okay. So up to now, can anyone think of an easier way to generate image? Okay, so up until now, we have learned that this point represents the actual image in the latent, in a high dimensional space. And I've told you that we will use a neural network to actually learn these directions. So you start off with a random image, and then you use a neural network to learn these directions from every single possible point in this space. This is the target. So this is the actual image that you want to arrive to. this is where you are. So because you start off with a noisy image, and you train a neural network to learn every single arrow. So if you're in here, you can fit into your neural network, and your neural network will point you towards this data point in here. So this is what I have told you. Can anyone think of an easier way to generate an image? Okay, so let me repeat what I've just talked about. So, essentially, so essentially, in diffusion model, we try to generate an actual image that looks realistic. So recall what I have told you about. So let's go back all the way back to here. So in the real world, we have this true data set, right? For the x-axis, in this example is height, but in the image example, this is the value of a pixel, right? So in the real world, there is often some kind of distributions that represent the true pixel value. So, say for example, this image, if I pick out one pixel in here, which looks kind of green, the say true distribution of say this pixel here green will have some kind of distribution, right? And for the diffusion model to start, we start off with a random noisy image. So, but in here, I've just told you a method that you can start with a random image, say in here, and then you will have your neural network to predict this kind of directions towards the real data in here. So can anyone think of a simpler way to do it instead of predicting instead of telling the neural network to generate this vector? Can anyone think of a better way to do it? So the goal is to move this point to here. Okay, this is the goal. And someone think of it. Oh, maybe I would use a neural network to generate this arrow. Can anyone think of a way to use a neural network to move this point to this point? Okay, so the answer is actually pretty straightforward if I told you. Okay, so the answer is actually why not? We trained a neural network to predict the noise instead of trying to predict the arrow. So why not we directly try to predict the noise instead of starting from the noise and move towards the data? If the idea is if we can actually use a neural network to predict the amount of noise that is actually producing on the directions, you can simply subtract the noise from the image. So this is what the denoising diffusion probabilistic model is. So The answer to that question is DDMP choose noise prediction instead of predicting the arrow itself. So if you use a neural network to directly predict the noise, because it is easier and more stable to train, while remaining mathematically equivalent to the score prediction. So essentially, if you have tuned some of these hyperparameters, you can sort of tell the neural network to directly predict the noise instead of the function, the score directions. So in DDMP training, we know exactly how noise is injected, so we can directly supervise the neural network with a clean mean square error objective. So the training procedure becomes more straightforward in sense. So sample a real image and then add no noise to form the noisy image and train the neural network to recover the exact noise. So epsilon is the pure Gaussian noise vector that is deliberately injected to the image. So you have your training set data. Okay, so during inference, the generation starts from a pure Gaussian noise from t step down to 1. And then using your neural network, you try to compute the noise and then subtract out the noise. So this is the noise that your neural network generates. So this is the parameter of your neural network, and this is the time point of your neural network. And this whole term is the predicted noise. So given this image with noise, you subtract out the noise and you get a clean image. This term here is actually another part of the noise. Is a fresh, also a normal distribution noise, and it's kind of adding some exploration term for the inference. So for every image that you create with this method, even with the same seed, you get a different image. So that's why you cannot reproduce or keep consistently generate the same image over and over again, because fundamentally you have this term during the generations of image. So let me clarify the training phase and the generation phase. So during the training, so you directly randomly inject different level of noise into the image, and then you train it once. So you train it once per sample. During inference, instead of going straight all the way from T to T naught, you kind of do it step by step in here. And you also introduce some noise during inference. So, anyone spot any problem with this schedule? Okay, so let's start over again. So from the beginning, I've told you that the main objective is to move this point to this real image point here. And I've told you that with DDMP, you can directly subtract the noise. So you're still kind of predicting this error, but in a sense that you actually predict this noise and subtract it. So directly go from here to here with different noise level. And during training, you do it all the way. So you do it, you train the input is this noise and target is this noise. The target is this one. So you directly train your neural network to move this point towards this center point. However, I told you that at inference, we kind of do it differently. So why can we not directly go from T0 to T0? If the training objective is what I've told you, going from one point directly go to here. So at inference time, it's actually going one step. So if this arrow is pointing towards here, at inference time, I will go one step here and add some noise, say here. And then second time for inference, I will follow the arrow, say here, and then I will add some noise to here. And I will do it again. So the direction is here, and then I will add some noise, maybe say here. And for now, I will go towards here, add some noise and here. And for now, I will go from here and add some noise to here. So this is the inference time. So if I trace my path, it actually looks like this. And to reshape. So during training, we jump directly from x0 to a random xt and predict it over noise. During inference, we never actually jump from clean one shot. We only take a tiny reverse step. So why does the training target still work for incremental denoising? So actually there is no mismatch. So the training teaches a direction field over all the noise level, and inference integrate the field step by step. So essentially, go back to this one. So if you jump all the way, because in here, the direction only tells you, say, somewhere along this line, but it does not actually tells you how far you should jump, right? It only tells you the direction, and kind of the magnitude. If you go all the way directly from this T level, so this T, and in here, in this location, it's actually different from here. So essentially the direction changed. So all you can do is kind of doing some movement and trying to gather as much information as possible for the direction you need to get into this point. So essentially, at inference time, you kind of doing something like this and try to get the overall sense of where this point actually lies. Okay, so there is essentially no mismatch between the training and inference. the training target is to pick a random noise level at t, corrupted to t xt, and ask the model to predict the exact noise used. And inference behavior start from the maximum noise level, repeatedly take a small denoising steps, one step at a time, using the neural network that you have got, and subtract out noises. So, okay. So these are the terminology. The big T often represent the maximum noise that you can inject. And these are the parameters that you might need to tune if you are going to train diffusion model. So I will skip that, and I think I can skip that also. I will leave you to kind of understand what these, you can understand these kind of slides at home. So essentially, the training examples start from an image, and then you sample a Gaussian noise, and then kind of inject the noise into the image. And then you use a neural network, a unit noise predictor, to predict, to actually train this objectives and predict this noise. And the target is, so epsilon is this matrix, which is the same as this one. And then your neural network output this noise, and the training objective is to minimize this noise. Okay. Okay, so these are just numerical examples you can go through. It's pretty straightforward. You just plug in the numbers. Nothing so special about this one. Okay. Okay, so we have introduced DDMP, doing this iteratively, and now another idea came along. You see in here, we often inject a noise during the sampling, so during the image generation, this term in here. And DDIM, which is another branch of methodology, suggested, oh, why not we just set this parameter to 0? So if we set this parameter to 0, essentially we will have less exploration kind of maneuvers. And if we set this term to 0, the image that is going to be generated is implicit. So that's why it is called denoising diffusion implicit models. What it actually does is this. So remember, we follow a trajectory. So say at this point we go according to our neural network compass. So we step one step towards here, and then we add noise like this, and then we iteratively in a way like this one. In DDIM, you actually just follow the direction that you have told. So this one, 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 and you reach your data point. So essentially, DPIM just said that, oh, we don't want, we do not want the stochastic term here, and to make our kind of trajectory smoother. Okay. And this is actually the mathematics that support this kind of more smooth analogy. Okay, so as I have mentioned, DDMP, which is juggling around because at inference time it will add some noise, and it finally reach this destination. For DDIM, it will just go straight to this point. However, it loses some kind of explorations trajectory. So can anyone tell me that why DDMP want to move around like this? So why does the original model suggest this one? But later someone told you, oh, maybe we should just go straight. But why in the first place? What is the main advantage, or what is the disadvantage of going directly straight? So essentially, for empirical reasons, there are not much disadvantage going straight. But in the first time, because the model parameter is not as large, we want to go all the way like this is because if you are in here, you use your neural network to predict the direction towards here once. And that's why if the contour or if in the high dimension space, it is not as smooth. Going like this is actually an advantage to find the global optimal terrain. So imagine if this is a flat plane, of course going from here to here is much more straightforward. But if the plane is not as kind of smooth as like this one, going here gives you actually some advantage to explore some other paths. So, but DDIM actually performs better. As I've mentioned, you kind of lose this wiggling movement, which is you lose some exploration. Okay, but it turns out it's actually not so important to explore the space. So models nowadays prefer DDIM.
Does it matter the number of things? As much as we have large having a low resolution
Yeah. Yeah, probably if you have. So, Cora asked a very good question. Is that so? Would the image with higher pixels change the contour of this space such that DE and P will have an advantage of maneuver through this one?
This sets out all the possible changes from one zone to the other. So it will construct these
Okay, so I think the question essentially boils down to, I think it's a very good question. And I think of course, the intuitive way to think of with the higher dimensions, space is more complex, such that this movement actually have advantages. I think with a high dimension space, I think more movement might help, but from empirical experiment, DDIM is just much better. So I think you can try it out. But modern diffusion models would often convert the higher resolution image into a latent space first before the diffusion. So it might be a good kind of experiment to work on. Thank you. Okay, so to summarize, DDIM sampling converts the stochastic reverse diffusion process into a deterministic probability ordinary differential equation, which makes the generation reproducible from the same latent state. And for DDIM formulation reduced sampling from 1,000 stochastic steps into just 20 to 50 deterministic steps. Okay, so can anyone tell me what is missing from this image generation method? Or another example, or another question is, what image can you generate from DDIM? The format is not important. Okay, actually, what I want to say is the method that I have just introduced, you have no way to control the image that you are generating. You cannot type in, I want to generate a cat, and it will generate a cat. All you can do is input a noise and hope that it generates a cat, right? So what is missing is actually how to generate an image with text, right? So DDIM tell us how to update from this XT. So denoising step, and in order to generate an image with text, we need another skills called classifier-free guidance, which tells us the noise predictor to use for that update when we have a text prompt. So in here we have the text the classifier free guidance to kind of detect a better noise that will point to the image that we want to generate. Okay, so I will give you a short break. And if you have any questions, feel free to ask during the break.